Good evening, ladies and gentlemen. I always have to say that I'm not an astrologer. You'll get no horoscopes from me. But towards the end of this talk, I am going to look forward into my very cloudy crystal ball and share some hopes and fears on what our lives might be like 50 years hence. But I am an astronomer, and I'll set the scene by saying something about a cosmic perspective. Let me see. Yeah. Right. Astronomy is the oldest science, except perhaps for medicine. And at the risk of offending any medics here, I claim it was the first science to do more good than harm. Ever since ancient times, it's been crucial for the calendar, for timekeeping and navigation. And it's the grandest of the environmental sciences. Indeed, the night sky is the only part of our environment that's been shared by all humans throughout history. They've all looked up and wondered at the stars and interpreted them in their own way. But as a science, astronomy is slightly more recent, and it took a big step forward here. This is my college in Cambridge, through the work of the best student we ever had, Isaac Newton. Trinity's been in decline ever since. There's been no one as good as him. But I have to say that though he was an unparalleled intellect, he was a most unpleasant man, solitary and reclusive when young, vain and vindictive in his later years. But he did design the first reflecting telescope, and he must have thought about reaching for the stars, because this is a picture from the English version of his great book, The Principia. And it's still the neatest way to explain the concept of orbital flight. He calculated that for a cannonball to achieve an orbital trajectory, for its trajectory to curve downwards no more steeply than the Earth curves away underneath it, its speed must be 18,000 miles an hour, far beyond what was then achievable, of course. And as everyone knows, the first object to achieve orbital speed was Sputnik 1, launched by the Soviets in 1957. 4 years later, Gagarin was the first man to go into space, and only 8 years after that, we had this familiar, iconic picture. And this was only 66 years after the Wright brothers' first flight. And I cherish this picture, signed for me a few years ago by 7 of the Apollo astronauts. It's not signed by Neil Armstrong, but I did meet him, actually. He, in fact, was sitting in the front row taking notes when I once gave a lecture in Philadelphia. At least I thought he was taking notes. He might have been doing the crossword or something, I don't know. But, of course, this was a heroic episode. And had the momentum been maintained over the next 40 years, after Apollo, there would be footprints on Mars by now. But after Apollo, as we know, the political impetus for manned spaceflight was lost. And it was a long time ago. Ancient history to today's young people. My students in England know that the Americans landed on the moon. They know the Egyptians built pyramids. But both enterprises seem driven by equally arcane goals. Because since 1972, people have done no more than circle the Earth in low orbit, more recently in the International Space Station. But space technology, without people, has of course burgeoned for communication, environmental monitoring, sat-nav and so forth. We depend on it every day. And for science, it's been crucial too. Telescopes in space and probes to the other planets, bringing back pictures of varied and distinctive worlds. So let me give you a quick tour of the solar system. This is a picture taken on the way to Mars, looking back from 5 million miles at the Earth and the Moon, where the sun's coming from the right. When you get to Mars, here are some pictures taken with the European Mars Express. This is a gorge several kilometers deep. This is evidence for some changes, sort of landslides on the surface. Things are changing from month to month. And, of course, in August, the Curiosity rover landed, and for the next 10 years, it'll be trundling around on the surface of Mars. It landed in the top left, and it's going to be going through this vast crater, ending up climbing the geological strata of the mountain in the middle. Going beyond to the outer solar system, here's Jupiter. The 4 moons discovered by Galileo all have been observed close up, and they're all very different. This is Io, sulphurous and volcanic. This is Europa, covered in ice with probably an ocean underneath, and there's a close-up of some of the ice. Going still further, the Cassini spacecraft went to Saturn. It sent back this wonderful picture from beyond Saturn. This shows an eclipse of the sun by Saturn. The Cassini is beyond Saturn, lined up, so that Saturn blocks out the sun, and you can see the rings in sunlight. That's a beautiful picture. Here's another picture. Something else that Cassini did was it carried in its cargo bay a small probe called Huygens, a robotic probe that was supposed to land on Titan, the giant moon of Saturn. And indeed it did. Titan has an atmosphere, it lands with a parachute. On the way down, it took the two pictures, the left and the middle. The right is where it landed. Now, this might look a rather nice place, rivers and a little lake, but the temperature's minus 160 degrees centigrade, and those rivers are liquid methane, and those lumps on the right are lumps of methane ice. Well, I hope that during the coming decades, by 2050, the entire solar system will have been explored and mapped by flotillas of tiny robotic craft. But will people follow them? This is Harrison Schmitt, one of the last people on the moon, 40 years ago. And I think the practical case for sending people back into space gets ever weaker with each advance in robotics and miniaturization. Indeed, as a scientist or practical man, I see little purpose in sending people back into space at all. But as a human being, I'm an enthusiast for manned spaceflight. And I hope some people now living will walk on Mars. They may be Chinese. China has the resources, the dirigi's government, and maybe the willingness to undertake an Apollo-style program that leapfrogs what the Americans did. But if others boldly go to the moon and beyond, I think it's more likely to be via cut-price ventures, spearheaded by individuals prepared to accept high risks, perhaps even one-way tickets. When I'm a bit older, I'd accept a one-way ticket. And they'd be driven by the same motives as early explorers, mountaineers, and the like. And that's why I'm hugely enthusiastic about Elon Musk's SpaceX company and other companies fronted by entrepreneurs with resources and high-tech expertise. By the way, I think the phrase space tourism should be avoided. It lulls people into thinking that such ventures are routine and low risk. And if that's the perception, the inevitable accidents will then be as traumatic as those of the space shuttle were. Instead, these cut-price ventures must be sold as dangerous sports or intrepid exploration. And they'll just be for the few. Don't ever expect mass emigration. Nowhere in our solar system offers an environment even as clement as the Antarctic or the top of Everest. Space doesn't offer an escape from Earth's problems. But having said that, a century or two from now, there may be small groups of pioneers living independently of the Earth, on Mars or on asteroids. And whatever ethical constraints we impose here on the ground, we should surely wish such pioneers good luck in genetically modifying their progeny to adapt to alien environments. And that'll be a step towards a divergence into a new species. The post-human era would then begin, perhaps only in a few hundred years. And this leads to one of the great unknowns. What creatures might be out in space already before we get there? No one expects much in the solar system. There are a few places here where there might be some life, but no one expects anything very advanced in these locations. But now, let's widen our gaze from our solar system to the world of the other stars, far beyond the reach of any probe we can now conceive. Prospects are here far brighter. We've now learnt something that makes the night sky far more interesting than it was to our forebears. We've learnt that the stars aren't just twinkling points of light. Many, perhaps most of them, are orbited by retinues of planets, just like the Sun is. This is a really fast-moving field of science. And these planetary systems display a surprising variety. Sometimes you find planets as big as Jupiter orbiting very close to their parent star, so their year will be a few days. Some are on very eccentric orbits. Several planets are orbiting binary stars, so they'd have two stars in their sky. And just in a newspaper today, I read about a discovery of a planet that would have 4 suns in its sky. So a remarkable variety already being found, a very exciting subject. But essentially all this evidence about planets around other stars comes indirectly, not by seeing the planet, but by seeing the effect of the planet on the motion or the brightness of the star it's orbiting. And I just want to talk about one technique, the technique where you look for changes in the brightness of the star. And this theory here is very simple. If a planet moves across in front of a star, it blocks out a bit of the light. So if you measure the brightness of the star, it'll drop a little bit when the planet's transiting. If, for instance, you looked at a transit of the Earth across the Sun from a great distance, the dip would be 1 part in 10,000. And the Kepler spacecraft, launched 3.5 years ago, has been pointing at the same part of the sky and measuring the brightness of about 150,000 stars in that part of the sky to a precision of 1 part in 100,000, and doing that several times an hour for each of them, looking for cases when you see these periodic dips, indicating a planet whose orbit's in the plane of the sky going across. And this is the way in which we have found huge numbers of planets, or at least found their shadows. Again, we haven't seen them directly. But we would, of course, really like to see these planets. This is just a movie of what we'd like to see. And that's very hard. To realize how hard, let's suppose there were some aliens out there, say 30 light years away, and suppose they were looking at our solar system with a very big telescope. To them, the Sun would look an ordinary star. And the Earth would look, in Carl Sagan's nice phrase, as a pale blue dot, very close in the sky to its star, our Sun, and billions of times fainter. But if the aliens could look carefully at the pale blue dot, they could learn quite a bit about it. The shade of blue would be slightly different, depending on whether the Pacific Ocean or the landmass of Asia was facing them. So they could infer that there were continents and oceans, they could infer the length of the day, and something of the climate and seasons, and maybe by looking at the light very carefully, something about the atmosphere, and that there was oxygen and ozone. Well, we can't do this yet, but within 20 years, telescopes like this will be able to do just that sort of thing for Earth-like planets around other stars. This is a telescope which the Europeans hope to build, where the mirror will be a mosaic 39 meters across. That's about twice the width of this room, really huge. And that will be able to do this sort of thing within 1 or 2 decades. Well, will there be life on any of these extrasolar planets? We can't assess the odds. Indeed, how life began on Earth is still unfinished business for scientists. We don't know. It could have been inevitable, or it could have been a rare fluke, like shuffling a deck of cards and ending up with them in perfect order. I hope we'll understand by 2050 how life began on Earth. And that, of course, will give us some handle on how likely it is to have arisen elsewhere, and also clues as to where to look. Even if simple life were common, and it may be, it's of course a separate question whether on these other worlds it's likely to have evolved into anything we might recognize as intelligent or complex. And it might be too parochial to focus on Earth-like planets and creatures like us. Science fiction writers, of course, have many other ideas. Balloon-like creatures floating in the atmosphere of Jupiter-like planets, swarms of intelligent insects, nanoscale robots, and all kinds of things. And incidentally, I would advise students it's better to read first-rate science fiction than second-rate science. It's much more fun and no more likely to be wrong, and it stimulates your imagination. Well, I'm not holding my breath for the detection of extraterrestrial intelligence, but I'm glad some people are looking. If we detect a signal as plainly artificial, then even if it's very boring, a list of prime numbers or the digits of pi, then it will carry the momentous message that concepts of logic and physics, if not consciousness, aren't limited to the hardware in human skulls, as it were. I don't think we know yet. But I wanted to mention that, of course, there are some people who think they do know the answer. They're the people who think they've been visited by the aliens and they've seen the UFOs. And I get letters from such people. It's one of the results of being Astronomer Royal. And I tell these people two things. First, I ask them, is it really likely that if these aliens had made the huge technological effort to cross interstellar space, that they would just meet a few well-known cranks, despoil a few cornfields for corn circles, and go away again? I think it's unlikely. And the second thing I tell them is to write to each other and not to me. Well, we might find ET, but perhaps ET doesn't exist. Earth's intricate biosphere may be unique, and that may disappoint the searchers, but it would have its upside, because it would entitle us to be less cosmically modest, because our tiny planet could then be the most important place in the galaxy. Perhaps even a seed from which life in the far future could spread through the galaxy. The philosopher Wittgenstein famously said, "If a lion could speak, we couldn't understand him." So even if we found aliens, would the culture gap with them be unbridgeable? I don't think it would necessarily. They may come from planet Zog and have 7 tentacles, but science would be a common cosmic culture. They'd be made of atoms just like us. They'd gaze out, if they had eyes, at the same cosmos. They'd trace their origins back to the same Big Bang. But of course, if we get a signal, we've got plenty of time to think of a good response, because signals take many decades to get there and back, so there's no scope for snappy repartee, as it were. But we could talk about the cosmos, so let me now offer a few comments on how we are probing the cosmos on the wider scale. First, a few words on stars. We understand a lot about stars, how they form in places like this, the Eagle Nebula, where new stars are condensing from dusty gas. We also see stars dying. This is what the sun will look like in about 6 billion years. And bigger stars die explosively. This is a famous object. Many people will recognize it. It's called the Crab Nebula. It's the expanding debris from an explosion of a star, supernova, witnessed by Chinese astronomers in the year 1054 AD. Some people here can perhaps read this, but I've been told this is the record of the Emperor's court astronomer, saying that the guest star had appeared in the heavens, brighter than the moon, and disappeared after a few weeks. And when we look to that place in the sky, we see 1,000 years later this. Now, you might think these supernovae are far away and long ago and irrelevant, but were it not for these, we wouldn't be here. That's because stars, during their lifetime, derive their energy via nuclear fusion. They turn hydrogen to helium, into carbon, into oxygen, etc. And then they fling it back into space. And then from that debris, new stars form. So all the atoms in our body were forged in ancient stars that lived and died before our solar system formed. Indeed, almost certainly each of us has atoms in us from hundreds of different stars from all over the galaxy. So we are literally the ashes of long-dead stars, or if you're less romantic, we are the nuclear waste from the fuel that made stars shine. And our galaxy is like a sort of ecological system where gas is being churned from one generation of stars to another. If you could get 2 million light years away from the Earth and look back, we'd see our galaxy looking like this. This, of course, is Andromeda, the nearest big galaxy to us. It's a disk viewed obliquely, where 100 billion stars are orbiting around a central hub, in the middle of which lurks a black hole weighing 30 million suns. And these galaxies are the main ingredients of the large-scale cosmic scene. Here's another one. This is the Whirlpool galaxy. Now, we can see lots of galaxies like this, and you might ask, how can we learn anything about them? Because they take about 100 million years to turn around. We can't experiment on them. If we are studying particles, we can crash them together in an accelerator and see what happens. We can't do that with galaxies, except that we can in the virtual world of our computer. We can model two galaxies, the gravitational pull of every star and every other star, and see what happens. And this is a movie showing that. Two galaxies are falling together, and you get a sort of train wreck. And it comes a mess like that, and this will settle down into one big amorphous galaxy. I should warn you that the Andromeda galaxy I showed is going to crash into our galaxy in about 5 billion years. And our galaxy will end up looking like this. Now, we can look up into the sky and look at lots of galaxies, and we see some like, like this. This is a real picture of two galaxies. And having done those sorts of calculations, which are speeded up by 10 to the 15 from real time, we can infer that what's happened here is two galaxies have got dangerously close, and each has raised tidal plumes on the other. And if we came back in 100 million years, we see these two having merged. So we can understand galaxies by modeling them and then looking at examples. There are huge numbers available for study. And we can also see what they were like in the past by looking far away and therefore far back. This picture shows a little patch of sky, a patch so small it would take 100 patches like it to cover the area of the full moon. If you had a small telescope, you'd see just a bit of blank sky. But with a big telescope, you see hundreds of smudges here, each one a galaxy, many fully the equal of our own or Andromeda, looking so small and faint because they're so far away. They're being seen distances of 10 billion light years when they've only recently formed. And this is observations out towards the limits of our observable universe. Now, one thing we've realized, and this was alluded to in the introduction, is that our universe, the physical reality, may be even bigger than we thought. We can look out to these galaxies 10 billion light years away, but we get to a horizon. The horizon is set by how far light's been able to travel since the Big Bang. But that horizon isn't anything real, any more than if you're in the middle of the ocean, the horizon around you is real. If you're in the ocean, you think the ocean goes on a lot further. And likewise, we suspect that the universe goes on a lot further than we can see. As in the bottom right here, we look out 10 or 15 billion years, but there are lots and lots of galaxies before. We have good reason for thinking that they go 1,000 times further, and they may go far, far further still. Indeed, if space stretches far enough, all conceivable chains of events could be played out somewhere, all combinatorial options. There'll be replicas of ourselves, Monkeys will type the works of Shakespeare, and whenever a choice has to be made, one of the replicas of ourselves will take each option. So if you make a bad decision, maybe it's a consolation that somewhere out, far beyond the horizon, you've got an avatar that's made the right decision. But that's not all. I've talked about that volume, which is the aftermath of our Big Bang. It may be that our Big Bang is not the only one. There's the idea of the multiverse, and that's depicted as a cartoon here, where this is our Big Bang, and there are other domains of space and time quite separate from ours. And the best studied of this is called eternal inflation, where Big Bangs are continually popping off in an expanding substratum. Well, this is all very speculative. Firming it up requires understanding the physics of the early hyperdense stage of the universe. So I put a hazard sign here because this is not well established. We can actually confidently extrapolate the universe back to when everything we can now see with our telescopes was squeezed down to the size of a solar system. At that time, each particle would have the same energy as we could produce in the LHC at Geneva. But all the key properties of the universe were laid down much earlier still, when the universe was that big. And I like this cover of this journal, which says that the universe was once that big. And that's when many key features of the universe were, we suspect, imprinted. So we've learnt that we live in a solar system that's just one planetary system among billions, in one galaxy among billions. But perhaps further Copernican demotion confronts us. The entire panorama that astronomers observe could be just a tiny segment in the aftermath of our Big Bang, which is in itself just one Big Bang among a perhaps infinite archipelago. And incidentally, what we think of as universal laws may, in this even grander perspective, be just parochial bylaws in our cosmic patch, a patch that happens to extend more than 10 billion light years around us. Well, it's exhilarating that these concepts are not just metaphysics, they're speculative science, but they're within the scope of scientific inquiry. And I think within 50 years, we will perhaps be able to say firmly whether we are part of a multiverse. But we're still groping for the truth, where in the fashion of ancient cartographers, we must still say, "Here be dragons." We confront Donald Rumsfeld's famous unknown unknowns. And what a pity, incidentally, that he didn't stick with philosophy. If I needed a logo for my area of research, I'd choose this. It's called an Ouroboros. It depicts the interconnectedness of the microworld on the left, of neutrons, atoms, and cells, and the cosmic world of stars and galaxies on the right. And we learn a great deal about the unity of things because of the links between left and right. The everyday world is determined by atoms, how they stick together to form molecules. Stars are powered by the nuclei within those atoms. There's a link there. And though I haven't had time to discuss it, we believe that atoms, the galaxies are held together by dark matter, which is made up of some subnuclear particles left over from the Big Bang. So there's a link there. The left-hand side here is the domain of the quantum. The right-hand side is where gravity and Einstein's theory holds sway. And those two theories, gravity and quantum theory, are the two great pillars of 20th century science. But they haven't yet been meshed together into a single theory. And in most contexts, this doesn't matter, because the domains of relevance don't overlap. Astronomers can ignore the quantum fuzziness in the orbits of planets because they're so big. Conversely, chemists can ignore the gravity between the atoms in a molecule because they're 40 powers of 10 weaker than the electric forces. But if you want to understand the very beginning of the universe, when the universe was itself very small, then we do have to have this unified theory. we need to have the unification symbolized, as it were, gastronomically here, because when the universe is very small, quantum fluctuations could, as it were, shake the entire universe. So to confront the overwhelming mystery of what banged and why it bangs, we need this theory, sometimes called the theory of everything. We ourselves, here, are midway on a log scale between atoms and stars. We're large enough compared to atoms to have lots of complexity, but not so large that we're crossed by gravity. And we are actually midway. It would take as many human bodies to make up the sun as there are atoms in each of us. The geometric mean of the mass of a proton and the mass of the sun is 50 kilograms, within a factor of 2 of the mass of each person here. And so to understand ourselves, we need to understand the atoms we're made of. We also need to understand the stars that made those atoms. And I mentioned the frontier of the very small and the very large, unified up here. But there's a third scientific frontier, the very complex. And this is, in a way, the most challenging one. Even an insect, with its layer upon layer of complexity, is harder to understand than a star or an atom, where intense heat and compression in a star precludes complex chemistry. This, incidentally, is the famous flea drawn by Newton's least favorite colleague, Robert Hooke, who was the pioneer inventor of the microscope and a wonderful draftsman, and he produced this book in the 1660s, drawing the flea and other insects through his microscope. So unified theories of the very large and the very small, though, of course, a huge challenge to science, shouldn't really be called theory of everything. That's a hubristic and misleading term, because they're irrelevant to 99% of scientists who work on things that are very complicated. Most scientists working on things down here are not held up at all by not having a unified theory. They're held up because they're studying things that are just very complicated. And that, I think, is important. A certain modesty is needed on the part of theoretical physicists. The analogy is often given of a game of chess. Suppose you'd never seen chess being played before. Then by watching play a game, you could infer what the moves were, how the knight moved, how the bishop moved, etc. But in chess, learning how the pieces move is just a trivial preliminary to the progression from novice to grandmaster. Likewise, learning the basic laws that govern the elementary particles is just a preliminary to understanding how these manifest themselves in complicated structures, including the most complicated we know about, which are these things here. Nearly all scientists are reductionists insofar as they think that everything, however complicated, obeys the basic equations of physics. But even if we had a hypercomputer that could solve those equations for, say, breaking waves, migrating birds, or human brains, it wouldn't yield the kind of explanation we really seek. Phenomena with different levels of complexity are understood in terms of different irreducible concepts: turbulence, survival, alertness, and so forth. The brain is an assemblage of cells. A painting is an assemblage of chemical pigment. But in both cases, what's important and interesting is the pattern and the structure, the emergent complexity. Well, how far will we have got by 2050? 50 years ago, we didn't know if there was a Big Bang. Now, as I said, we can draw quite precise inferences back to a nanosecond. So in 50 years, debates that now seem flaky speculation may have been firmed up. But, and here I'm perhaps sticking my neck out a bit, I think we should recognize that at some stage we might, as it were, hit the buffers, because our brains just don't have enough conceptual grasp. After all, our brains evolved to cope with life on the African savanna where our remote ancestors lived, and they haven't changed much since then. And it's surprising, therefore, that we've got so far in understanding the counterintuitive microworld of atoms and the vastness of the cosmos. But just as a monkey can't grasp quantum mechanics, there could be aspects of reality, unified theory or consciousness or something, whose elucidation must await some post-human intellect. Maybe these intellects are out there already. If not, they might emerge in the far future. Now, let me focus back on the Earth, as I will for the rest of my talk. I've lived my life among astronomers, and I can assure you that their awareness of vast expanses of space and time doesn't make them any more serene in their everyday life. They fret as much as anyone else about tomorrow and next week. But there is one special perspective that astronomers can offer, and that's an awareness of a vast future. The stupendous timelines of the evolutionary past, as in this time chart, are now part of common culture, except maybe in Kansas or parts of the Muslim world. But most people still somehow think that humans are the culmination of the evolutionary tree. We are the end of it all. And that hardly seems credible to an astronomer. I'll tell you why. As this time-lapse illustrates, our sun formed 4.5 billion years ago. It's a bit less than halfway through its life. It'll be 6 billion years before it flares up, engulfing the inner planets. And the expanding universe will continue, perhaps forever, destined to become ever colder, ever emptier. To quote Woody Allen, eternity is very long, especially towards the end. So any creature witnessing the Earth's demise 6 billion years hence and sending this postcard, they won't be human. They'll be as different from us as we are from a bug. Post-human evolution, here on Earth and far beyond, could be as prolonged as the Darwinian evolution that's led to us, and even more wonderful. Darwin himself was aware of this. But we can strengthen the conclusion because evolution in the future is going to be even faster than in the past. It won't be natural selection, it'll be on the technological timescale of genetic modification or machines taking over. But even in this concertina time span, stretching billions of years into the past and billions into the future, this century is a defining moment. We've had these images for 40 years. They're iconic for environmentalists. But suppose that the hypothetical aliens I mentioned earlier, who are watching our planet, had been doing so for its entire history. What would they have seen? Over nearly all that immense time, 4.5 billion years, Earth's appearance would have altered very slowly. Continents drifted, the ice cover waxed and waned, successive species emerged, evolved, and became extinct. But in just a tiny sliver of the Earth's history, the last 1/1,000,000th part, a few thousand years, the patterns of vegetation started to alter faster. This signals agriculture, the presence of humans on the scene. And then there were even more abrupt changes. The carbon dioxide in the atmosphere began to rise enormously fast, and something else completely unprecedented happened. Rockets launched from the planet's surface escaped the biosphere completely. Some went into orbit around the Earth, some journeyed to the moon and planets. Well, if they understood astrophysics, these aliens could have predicted that the biosphere would face doom in a few billion years, when the sun heated up and then flared up and died. But could they have predicted this sudden fever halfway through the Earth's life? These human-induced alterations occupying overall less than 1/1,000,000th of the Earth's elapsed lifetime and seemingly occurring with runaway speed. If they continued to keep watch, what might these aliens witness in the next 100 years? And the answer, of course, depends on us. The stakes are high between progress and catastrophe. Some years ago, I wrote a short book on this theme, which I entitled Our Final Century, with a question mark, and the publisher took away the question mark, as you can see. And then the American publishers changed the title to this, Americans like instant gratification, and perhaps the reverse. And my theme was that taking all risks into account, we wouldn't wipe ourselves out, but there was a 50% chance that we wouldn't get through to the end of a century without some disastrous setback. And just as a plug, I should mention my new book, which develops this in more detail. Over most of history, the threats to humanity have come mainly from nature. Disease, earthquakes, floods, and so forth. But this century is special. It's the first when one species, ours, has Earth's future in its hands and could jeopardize life's immense potential. We've entered a geological era called the Anthropocene. And the Anthropocene began, I suppose, with the advent of thermonuclear weapons. But devastation could arise insidiously rather than suddenly, through unsustainable pressure on energy supplies, food, water, and natural resources. Indeed, these pressures are the prime threats without enemies that confront us. Humanity's footprint is getting larger because we're becoming more demanding of resources, but also because there are more of us. This is how populations have grown over the centuries, very fast indeed, rising from 3 billion in 1960s to 7 billion today, and probably going up to between 8.5 and 10 billion by 2050. And most of the growth is going to be in the developing world, and the world's intellectual and physical capital is going to shift to Asia. It'll be the end of 400 years of European and North American hegemony. But the projected growth is slowing off a bit, because in many countries fertility has fallen to the replacement level of just over 2 births per woman. Indeed, in Europe it's only 1.4. And the falls have been dramatic in some places. In Iran, in 30 years, it's fallen from 7 down to 2. And this so-called demographic transition is a consequence of declining infant mortality, availability of contraceptive advice, women's education, and so forth. But numbers are still rising fast in some parts of the world. India's population is projected to overtake China's in 2030 and could exceed 1.6 billion by 2050. And there could then be 1 billion more people in Africa than today, where the fertility rate is still more than 7 in some countries. Global population seems a currently under-discussed topic. That's partly because doom-laden forecasts made in the past proved off the mark, and because it's deemed by some a kind of taboo subject, tainted by association with eugenics in the 20s and 30s, Indian policies under Indira Gandhi, and more recently with China's effective but hardline one-child policy. There's a campaigning group in England called the Optimum Population Trust, which tries to promote interest in these issues, and I belong to it. But I'm not sure that we can actually specify an optimum population for the world. That's because we can't confidently conceive what people's lifestyles, diet, travel patterns, and energy needs will be in 2050 and beyond. To take two extremes, the world couldn't sustain anywhere near its present population if everyone lived like present-day Americans. On the other hand, 20 billion people could live sustainably with a high quality of life if they all had a vegetarian diet, didn't travel, and interacted just by super internet and virtual reality. That particular scenario is neither very likely nor very attractive. But it is therefore naive to quote a single unqualified headline figure for the world's carrying capacity. But nothing barring catastrophe can stop a rise to around 9 billion by mid-centuries, and that's because most people now alive are still young. But we can influence the trends beyond that time, and enhanced education and empowerment of women within this decade is surely a benign priority in itself, but it would reduce fertility rates in Africa and India. And that is surely a good thing, because the higher the post-2050 population becomes, the greater will be all pressure on resources, especially if the developing world, where most of the growth will be, narrows its gap with the developed world in per capita consumption of energy and other resources, as we surely hope it will. Humans appropriate about 40% of the world's biomass already, and that fraction is rising. And the resulting ecological shock and extinctions could irreversibly impoverish our biosphere, and these risks are aggravated by climate change. We are destroying the book of life before we've read it. Biodiversity is a crucial component of our well-being. We're clearly harmed if fish stocks dwindle to extinction. There are plants in the rainforest whose gene pool might be useful to us. But for many environmentalists, these instrumental and anthropocentric arguments aren't the only compelling ones. For them, preserving the richness of our biosphere has value in its own right, over and above what it means to us humans. But despite these concerns, most experts claim that modern engineering and agriculture can provide food and energy for 9 billion. And other advances, especially in healthcare and information technology, offer bright prospects. But there's a downside, which I also discuss in my book. The same technologies that promise so much also open new vulnerabilities. For instance, global society depends on elaborate networks, electricity grids, air traffic control, international finance, just-in-time delivery, and so forth. And unless these are highly resilient, their manifest benefits could be outweighed by catastrophic occasional breakdowns cascading through the system. And the threat is terror as well as error. Concern about cyber attack by criminals or hostile nations is rising. And there are such concerns too in the bio area. Advances in genetics offer huge potential for medicine and agriculture, but already the genomes for some viruses, polio, Spanish flu, and SARS, have been synthesized. And expertise in such techniques will become widespread, posing a manifest risk of bioerror or bioterror. And we're kidding ourselves, incidentally, if we think that all those with technical expertise will be balanced and cautious. Expertise can be allied with fanaticism, and will be individuals with the mindset of those who now design computer viruses. The global village will have its village idiots, and their idiocies can have global range. So, the huge empowerment of individuals or small groups by fast-developing technologies presents, I think, novel hazards, and will highlight the tension between security, privacy, and freedom. The technologies I mentioned up to now are those that already exist. But what about new ones that could be equally disruptive and transformative? Scientific forecasters have a rather dismal record. One of my predecessors as Astronomer Royal said space travel was utter bilge, and few in the 20th century envisaged the transformative impacts of the silicon chip or the double helix. The iPhone would have seemed magic even 20 years ago. So looking 50 years ahead, we must keep our minds open, or at least ajar, to what may now seem science fiction. For example, human nature and human character have changed little for millennia. Before long, however, new cognition-enhancing drugs, genetics, and cyborg techniques may alter human beings themselves. That's something quite new and disquieting because it could portend more fundamental forms of inequality if these options were open only to a privileged few. And we're living longer. Indeed, a real wild card in population projections is that future generations could achieve a really substantial enhancement in lifespan. This is still speculation. Mainstream researchers are cautious about the prospects of more than incremental increases. But such caution hasn't stopped some people, worried that they'll die before this nirvana is reached, from bequeathing their bodies to be frozen, hoping that some future generations will unfreeze them, resurrect them, or download their brains into a computer. You could have this done in California, and as cut price, you could have just your head frozen, and not the rest of you. Well, I was once interviewed by a Californian group of these cryonic enthusiasts. Cryonics, they're called. And this society was called the Society for the Abolition of Involuntary Death. And I rather upset them by saying I'd rather end my days in an English churchyard than a Californian refrigerator. And they derided me as an old-fashioned deathist for saying this. What about robotics? Even back in the 1990s, IBM's Deep Blue computer beat Kasparov, the world chess champion. But robots can't yet recognize and move the pieces on a real chessboard as adeptly as a child can. So advances are patchy. But later this century, their more advanced successors may relate to their surroundings and to people as adeptly as we do. And then a new set of moral questions will arise. We accept an obligation to ensure that other human beings, and even some animal species, can fulfill their natural potential. So what's our obligation towards sophisticated robots? Should we feel guilty about exploiting them? Should we fret if they are underemployed, frustrated, or bored? Well, these are problems for the conjectural future, but as science empowers us more, there'll be a widening gulf between what it enables us to do and what it's prudent or ethical actually to do. That is my concern. But the biggest gap today is between what science allows us to do and what really happens in the political and economic world we inhabit. We don't need new inventions to improve the world, we just need proper applications of those we already have. And scientists shouldn't be bashful in proclaiming a hopeful message. We can truly be techno-optimists. The innovations that will drive economic growth, information technology, biotech and nanotech, can boost the developing as well as the developed world. And modern engineering and agriculture can feed us all. That's all good news. But of course, the intractable politics and sociology engenders pessimism. All too often, the parochial and the immediate trump the global in the long term. Politicians look to their own voters and the next election. Stockholders expect a payoff in the short run. Medical research focuses on diseases of the rich, not enough on tropical diseases. There's a current slogan in England called, "We are all in this together." It's received with a certain cynicism by many of us. It comes from David Cameron. But we need to realize that we are all on this crowded world together. Problems caused by shortage of food, water, resources, and the transition to a low-carbon economy can't be solved by each nation separately. So the question is, can our sympathies become more broadly international? Can our institutions prioritize projects which are long-term by political standards, even though a mere instant in the history of our planet? Well, I want to close with a bit of preaching, a personal perspective which strikes me whenever I visit the vast and ancient cathedral of Ely, which is just about 10 miles from where I live in Cambridge. This is 900 years old. Most of its builders had never travelled more than 50 miles. The fens were their world. Even the most educated knew of essentially nothing beyond Europe. They thought the world was a few thousand years old and that it might not last another 1,000. But despite these constricted horizons in both time and space, despite the deprivation and harshness of their lives, despite their primitive technology and meager resources, they built cathedrals, though they knew they might not live to see them finished. And their legacy still elevates our spirits nearly a millennium later. What a contrast this is to so much of our discourse today. Unlike our forebears, we know a great deal about our world, and indeed about what lies beyond. Many phenomena still make us fearful, but the advance of science spares us from irrational dread. We know that we are stewards of a pale blue dot in the vast cosmos, a planet with a future measured in billions of years, whose fate depends on humanity's collective actions. But all too often, our focus is short-term and parochial. We downplay what's happening even now in impoverished, far-off countries, and we give too little thought to leaving a fair inheritance for our grandchildren. So we do need to broaden our sympathies in both space and time, to perceive ourselves as part of a long heritage and stewards for an immense future, and to be guided by the best science, but also by values that science itself can't provide. The future is up to us. And just to finish with, I want to quote from the great biologist Peter Medawar. he said this, I quote, "The bells that toll for mankind are like the bells of alpine cattle. They are attached to our own necks, and it must be our fault if they do not make a tuneful and harmonious sound." Thank you.